And that is the class number, practical class number 5. Yes, number 5. Number 5, and we can continue to design your very airplane. And your life is about to become more hard and hard right now. You see, in front of you, you see step 3, geometry of airplane. Very short. Remind you what we did. In case you watch this video not by one, no, due to some reason. Remind you what you already did. You already all did. You have got the task. How to work with tables of tasks. Task it will be later. You has got the task, and task said create passenger airplane for amount of people for such a range. In examples that we are trying to play with right now in front of you, we have 100 of people and range 3,000 kilometers. On 3 points, we know nothing else by now. Before we get started. Now we know a little bit more. What we did, using their idea of Majaysky, that airplane pieces, airplane different systems, all together they create takeoff weight, and they are of the same relative weights, approximately in the same class of airplane. No, it's idea of Majaysky developed by Bolkhovitinov, and we have a formal equation of Majaysky relative weights equal to 1. What we did first, we have studied experience of another engineers who already have proven their decisions, airplanes that already fly, approximately of the same class, and we have collected statistical data. I took approximate table with statistical data that you're supposed to do either next. And what do we interested in? Above the all, we're interested in mass parameters, in parameters of airplane masses. I placed here relative masses on purpose. It's the same table, but you may do it without. You may fill this table only with weights of airplane, masses of airplane, and with parameters of geometry of airplane. With weights, we have been already working. We have analyzed the relative weights and made our own decision that in our case, distribution of weight will be like this between structure and equipment of the airplane. Remind you that it comes about so-called empty equipped airplane. It's include weight of structure itself, this forceful skeleton airframe. It's whatever sort of equipment, general equipment, it comes about electrical equipment, radio navigation equipment, so on, and some specific equipment, whether it's cargo, airplane, or passenger, it's already included into this mass. And plus to this, we have weight of the engine. And altogether, it's so-called empty equipped airplane. Why we use it? Because it's more simple to find it in internet or in some reference books that you are going to use about parameters of different airplanes. Next, crew. Crew, I also explained how to calculate. Next, payload. We have calculated relative weights, and we know absolute weight of our payload. Either it's cargo airplane and you are given immediately the weight of payload, or it's passenger airplane given in amount of passengers you need to carry to transport, and it means that 120 kilograms for one passenger multiply on amount of passengers. So the only place that known both in relative and absolute value, it's payload. And relative mass of fuel, which depends on the dispersion of ranges. The shorter ranges will correspond to the less relative masses of fuel, the longer ranges for more relative mass of fuel. Actually, it's very not much, it's around 5-7%. If we talk about civil airplanes, when it comes about military airplanes of different classes, it's quite another story. So we have narrowed our design game, let's say, by passenger and cargo airplane, which are rather similar. Now, after we have distributed the weight between system of airplane and knowing the absolute value of payload, In the zero iteration, we understand that our airplane equal to, in our example, 60 tons. What is next? Next, we need to go to jump from weights to geometry, at least again in the first iteration, in the first approach. And how we may do it? We used idea about balance of forces. We used this formula, which gave us some results, but they appeared a little bit less than we await, let's say. And that is why we use one more approach to check our decision, to detailize our decision. How? We, in our statistical data, have area of the wing, compulsory have it. And this area of the wing, we may compare with takeoff weight to understand specific load to the weight. It's so-called load to the 1 square meter of your wing in future. Analyzing the specific loads, we have chosen some value for our airplane, and finally we have chosen some area of the airplane wing. Do forgive me, already not remember which one, maybe 120 it was. Вот 120. Вот in calculator it's yet save it. 120 square meters supposed to be our wing. And now we need to design it. Once again, let's continue. First you need to select the shape of the wing. No, certainly I trust I'm not going to give someone supersonic airplane for passengers, so you have no delta wing in your choice, certainly. You have choice between so-called straight wing, conditionally straight, tapered wing, and swept wing. If you'd like, you may imagine whatever, if you'd like. But typically, when we analyze general appearance of passenger and cargo airplane, what do we see? Typically, if we're not talking about some fantastic concepts like Boeing or Airbus have created some flying wings or some even dirigibles, if we're thinking about traditional scheme, so it's usually either straight or swept, not tapered and swept. What it depends on. Once again, this beautiful face, I love it. Sorry, I scrolled it already. This picture. What it depends on. No, quite clear. Lift will be different. No, seems like coefficient of lift might be different. That may be compensated with different area also. But such wing, I need to another diagram actually. Such wing, straight wing, it's more appropriate for low speeds. We need another chart here, chart of the drag, not chart of the lift. Sorry, let's try to find it right now. This chart of the drag. Somewhere here. It's about lift. Ой. Так, тебя прибрать. Oh, do forgive me. I thought I'm ready completely. This place. Now, and here it's visible how shape of the wing affect to the drag. And we understand that if we're talking about the area up to 0.5, it seems like it's more profitable for us, more feasible. The green line, it's a straight wing. If we're talking about speed closer to transonic, then like 0.8, in the statistical data of airplanes that we used, they fly in speed 800, 900 kilometers. It's approximately correspond to 0.85, 0.86 Mach number. And we understand that in this case, maybe better to use swept wing. So depending on the speed, better to use either straight wing for low speed airplanes or swept wing for airplanes with high velocity. Speed maybe also I will detailize in your individual tasks. Maybe the ranges of speed I will detailize in order to make your life a little bit easier. In order don't make such a decision. So shape of wing for you will be somehow determined already, partially by me. Either it's straight or tapered or it's swept one. Because if I limit your range of speeds, it means that I limit you also in collecting of statistical data. So when you collecting data, you're also paying attention to the flight speed. No, maybe I'll limit you. Next, maybe someone will have task which is no limits. Next, we have chosen the shape of the wing, and now it's necessary to understand what are span of the wing and chords of the wing. We know only the area, but this area may correspond to different shapes. Yes? You do remember that, sorry, where it disappeared. Oi, where it disappeared this picture. That wing area calculated with including the area taken by fuselage. Like center wing is also considered like a wing. This picture you do remember. And let's continue. And for this we need to recollect about so-called relative parameters of the wing. First, wing aspect ratio. Dimensionless characteristic which show the practically it comes about the relative elongation of the wing. How long wing visually is. Oh, this picture. How long the wing? For speedy airplanes, it will be more short. For slow airplanes, beta gliders, it will be more long. It's wing aspect ratio. Here it's less value, here is greater value. Analyzing the geometry of airplanes that you took for statistical data, I strongly recommend you to calculate this wing aspect ratio. For the most laziest ones, but of course laziest ones, they will have less grades. You understand? At the end of file that I'm going to leave for you, no, with tips, let's say. Besides of wing loading, here some geometrical parameters given. So you may watch also here aspect ratio given in this. If you'd like, approximately find airplane in this list which is similar to your class and try to use it. But better, of course, to calculate, it's not difficult. To calculate your very own. Knowing even two parameters like what you see in my table here, wing area and wingspan, here, what wing area and wingspan, even without exact values of chord. By the way, this exact value of chord you might find approximately by proportions, at least. Like we all have pictures of those airplanes. Even the sort of drawings are given in internet. In English version only picture. No, in our versions I've seen even drawings of them. Or at least we might use option like design scheme, for instance. No, let it be A318 design scheme. Oi. What my majesty wrote. Oh, here is. Even by the sketch, it's possible, understanding that wingspan is, and we know the value that we have found already in internet, we may approximately by scale esteem what is the root chord and what is the final chord. And we have the wing area. Once again, remind you, wing area given in statistical data. Let's come back to story about that one. So even if you have no the value of chord, you see, you may find it. Knowing wingspan and knowing the wing area, we may calculate something. Look, wingspan, wing area, and we need wing aspect ratio, of course. Either you found it somewhere or you approximately may estimate on your own, once again. But what if your wing is not straight? How to calculate? What is there? Let me once again to show you point. All this we delete. We don't need it. When it comes about straight wing, everything is very simple. Why it's here is now. Everything is simple. We have span. We have chord. Так? And we are able to, in English it's called wing aspect ratio and designated like this. In our books you might find it with the name lambda, Greek literal, and it's like span to the chord. Span to the chord. Let it be. And one more variant is shown in slide here. Yeah, you see. It's for case when we have no equal chords, as you might see, in the root and the top, in the tip. In case you have swept wing, you may find so-called, here is, you see. In this case, you may find, but here they use another designation. Just notice it really. I took these pieces in different books that I'm already sent to you, and just on purpose to make you, to take your attention to those places. And what these places are about. Look, it's so-called mean chord or mean geometrical chord, may be called in some another literature. In our literature, it's called mean, not mean chord, but it's called average chord. In direct translation, it will be called average arithmetic chord. And in English literature, it's called usually mean chord. How it may be calculated? Either you calculate it knowing the wing area and wing span, you may calculate this mean chord, formulas you have seen at the top. And another way to calculate it, not to calculate it, but to obtain it geometrically, let's say, for the picture of real wing that you have, you may do some additional construction, let's say, and this additional construction may help you to understand what is the value of this mean chord and where is it. Because depending on the shape of wing, it will be in the different distance from the center of the wing. For some calculations, it's important. Now I show you the picture, and next I will try you to show how to do it in point. Pictures in order you understand where to find it, actually. Idea is in a simple geometrical, let's say, construction. Вот, давайте, like this. In case we have wing of swept shape, in case we have normal line, why it does not draw now? What some leading edge here, the line of leading edge, okay, trailing edge, the line of tip chord and root chord. How to find geometrically where this mean chord. Area from one side of mean chord and from another side of mean chord will be the same. And remind you, it comes about half of the span. In this case, here is from here to there, we have half of the span. it means that at this place you have line. No, it's called plane in our literature. It's called plane of airplane symmetry. Plane of symmetry of airplane. So fuselage is somewhere here already. I hope you understood. Very well. Area from one side of main chord and another side of main chord is the same. No, it's clear if we try to analyze straight wing. No? Where is the main chord? Here, in the middle. And areas in this place, areas are the same. How to calculate it here? Or you may calculate it really directly, because in case it's just tapered wing, swept wing, it's practically the taper, but this taper is a little bit distorted. It's possible to calculate. Or to simplify our life, what should we do? Look, we draw the line which equal to this. What, like we measure this size and we draw this line in another place. Here. Well, I did it. Like additional construction in the case. And at this place, near the tip, in contrary, we need to draw something that equal to the rod chord. Like this. No, it will be my measure. And additional construction is, here is, I added here the size of root chord. No, and next one, the most difficult action, join it. And here you have also one more line, one more line, mean line of chords, and the point of an intersection of them. So mean chord is, the chord in question is here. It's very simple, actually. It's just simple geometrical, not even calculation. Some seconds and you have it. In case you do it in scale, no problem to see the size at all. If you do it in some system for drawing, for instance. And once again, let's come back here. What do we see? What it's explained in this photo and in the book that you may open and read attentively. In case you do it, you will see the same explanation, how to find geometrically the value of mean chord. Once again, why this mean chord may be necessary in case you have not straight wing and you need to analyze next some parameters of wings. For instance, to calculate the span. To calculate the aspect ratio of the wing aspect ratio to calculate. In case you have no exact information about this. And in some our calculations also next, the mean value of chord is necessary. What in particular, where it's straight wing aspect ratio, it's like the same value of chord, it's quite clear. Yes. When it's swept wing, people usually use this mean chord, what like ratio between span and mean chord that we have constructed together. Now, in case you don't know it, see, please, how it's maybe determined by wingspan. You have wingspan in geometrical information and wing area. Very simple. Well, so we already understand wing aspect ratios, and approximately considering these, we may start design of your wing. Besides of wing aspect ratios that show additional elongation, we have one more coefficient that show you wing conditional narrowing in case you're going to use wing of swept shape or of tapered shape. Also do analyze it, and next use the same relative parameters. Your area of the wing may be differ depending on the variations, let's say, in statistics that you have collected. So sizes like wingspan will be not quite the same. You understand it? Yes? But if you not in contrary, what here what we did, we see the area, we have area and span, and we have calculated the aspect ratio for airplanes that been taken as statistical airplanes, let's say. And no, let's think that they approximately of 8, like wing aspect ratio is 8. And what does it mean for you? It means for you that if you're working, oh, so do forgive me, it's another portion of explanation, do forgive me, that if you decided to take some wingspan, for instance, taking the coefficient wing aspect ratio, you have designed it, you have decided it's wing aspect ratio that I'm going to use, knowing the area, you may calculate the span. Agree? Once again, here in this formula. If you have decided that in my class wing aspect ratio is equal to 8, and I have here what area of wings that I already know, so where is our calculator by the word, and it's necessary now to understand what is the wingspan. Out of this idea that we understand this value and this value, we may calculate the wingspan. No, let's try to do it together. Once again, where is the point? Let's copy formula. Wing aspect ratio. If you not mind, I will use our designations. I will use this wing aspect ratio as it should be in English. No, not should be, but as I have seen it in English books. I don't know how it's designated in your textbooks. No, I mean in Chinese language. In our, it's designated in with such a sign. And when you read the book of our Fedotov textbook, that I said it's too much first for you, of course, but it's enough if you need to find something, it's enough to open that. Oh my, how much I already sent you, poor children. Да, sorry. Fedotov textbook. It's called, it's started like general arrangement of airplanes. It's somewhere here. People, I will find it and remind you after the class because it takes so much to scroll it. Cave of the Wing is вот она, Fedotov textbook. Fedotov general arrangement. Да. In this book you may find some information about the story what we are talking about. Not exact technique like step by step, but some information. And in that book you will see designations that we get used to, like we teach our students in our country. So this one, wing aspect ratio equal to span. No, not idea how to call it because in different English literature it's called in different way, you see. And let's write by words immediately. Span twice, do forgive me, square it, and here is area of the wing. Area was 120. 120 area. Also, have not measured it, have not analyzed it. Let it be, guys, 8. Let it be 8. Wing aspect ratio, relative elongation of the wing, let it be 8. And span matter in question, of course, in square. What is it? What it should be equal to? No, question is. Well, let's use calculator because I need square root anyway. Sorry, seems like simple. No, you understand, it should be rewritten like 8 multiplied on 120. Span. Arithmetic is simple. And value is simple, but to not remember square root of this value. So we'll try to find it here immediately. Так, so 120 we multiply on 8 equal to, and no, almost 30 meters it will be. Oh, not 30 meters. Так, square root value. No idea how to do it. First, let me to check. Так, 4 square root. It's working contrary. Вот это, z1 maybe square root, да? Так, 4 square root to 16 square root. Great, it's work. And it, I already do not remember what it was here. On 8 and square root. Да, 30. Practically 31. No, so we has got span 31. By the word, let's compare to the airplanes that we have collected. Interesting. Look, approximately some in between, with Airbus, which a little bit greater than necessary by passengers, and a little bit more than Antonov, which is less than necessary in passengers. No, approximately, or the proper way, let's say, at least in our zero iteration. So let it be our span now is 30 meters. Wing area was 120 and span is 30 meters. I better, of course, should type it with words because next I will not remember what it was. 30 meters span. And now in backward calculation, we may approximately understand what is our mean chord, at least should be divided on 8, and we understand that mean chord is practically 4 meter, a bit less than 4 meter. And in case we use straight wing, it's already enough. No, like you understand that chord equal 30 to winged aspect ratio. Yes? If it's equal to wing aspect ratio, which is 8, as we agreed originally, it means it's a little bit less than 3. If you not mind, I do not calculate. Let's imagine it's approximately 3.8 meters. But in case you're going to work with swept wing, it's so-called mean value of the chord, and this mean value of the chord, what you might do next, you may use one more relative parameter which show you relative narrowing of the wing, and to work with the root and with tip, chords on the root and tip. But it means that when you're analyzing the statistical data, you also need to recalculate this relative narrowing of the wing for your statistical airplanes, for your prototypes. If not, then you may, let's say, do it voluntary because of different consideration. Because really design is not limited with these simple direct ideas like this. These things may help us at the first steps, but really next it may be changed, and may be changed due to different reasons, as I hope we will see. But right now, approximately at least we may understand values of our root chords, root chord and tip chord out of these values. What is next? What is next step? No, that one about wing geometry, I hope you understood. We select the shape, again considering prototypes, considering the range of speeds that you are working with, considering your own consideration, whatever they are. But do remember that it's important to follow to the rule right now on this step, on this stage. You do remember obsessive ideas of different groups of designers. Да? Those who are responsible for airframe have obsession with minimum of weight, minimum of mass. Those who are responsible for the aerodynamical performances, aerodynamical group, they are obsessed with the minimum of drag. So your considerations, whatever they are, they should be subordinated to the idea minimum of drag. And how this minimum of drag approximately may be realized, we have already seen. The less speed, the more straight wing. And also it's recommended that or another type of profile, of course, relative thickness of profile recommended for different speeds. And one more important consideration next will be where the fuel to hide, because in passenger airplane, you either need to place fuel inside of fuselage instead of passengers and cargo. No, not the way. So then you need to extend the fuselage in this case, you understand? Or you may hide fuel in the places which are relatively empty and they are not in fuselage. And what are these places relatively empty? The wings, of course. And typically, the wing is used for fuel tank and fin. Not stabilizers, but fin in big airplane may be taken with fuel tank. No, and some additional devices which are hidden in the fin and used only after catastrophic situations. I'm talking about so-called black boxes, which are actually not boxes and not black. They usually of orange color, and they usually of spherical shape. Devices for automatic registrations of flight parameters that at the final improper landing of the airplane may be found and read what happened. Well, do pay attention one more moment also here. What these pictures, very beautiful pictures, next will be what they about the effectiveness, efficiency of flight controls during some emergency situation in flight. What these plots talking about? I hope next will be more understandable. Here is shown swept wing and downwashing of the swept wing in case of increasing of coefficient of lift, increasing angle of attack. For straight wing, this downwashing has a bit another picture. No, that is once again, it's proven, it's checked, it's tested in real life, in wind tunnels, and so on. And what is known by now, that straight wing, the problem of stall, the problem of sharp reducing, the problem of increasing additional turbulence above its period. Yes, you do remember those vortex, these pictures and videos that I hope you do remember. I hope you have been watching this, at least together with me. The pictures and videos about aerodynamical problems that may appear due to increasing of angle of attack or due to improper shape when we have boundary layer separation from the airfoil, and in this case it's appeared turbulent zone immediately over the wing, and it's increased sharply and quickly to the front, and in this case lift just disappeared. But for one profile analyzing, it's like theoretical story. In real wing with end shapes, with not endless shapes, and depending on the shape of the wing, this stall appear in different places. This zone of increased turbulence appeared in different areas of the wing and in different places of the wing. What this picture show you, how it's appeared and progressing in their swept wing. In swept wing, it's usually rock immediately on closer to the tips due to the shape of the swing, due to specific of its downwashing, it's closer to the tip. That is better or worse? No, on one hand, it's not good because here we have flight controls, ailerons, and at the closer to the fuselage, we have what? We have here high lift devices, which are not so important during cruise flight. You understand that high lift devices been used only, no, practically they are used only during takeoff and landing. And the efficiency in cruise flight, it's not so dreadful, let's say, for us, because they are not working here. It's like general, they are hidden in general profile of the wing. And ailerons we use during the cruise flight, so not good. But on the other hand, if we have swept wing and this problem may appear at the end on little area, because here we have narrowed wing, it's not so dangerous because all other area is yet not affected with the stall, and you have time, in case this problem is identified, it's mentioned, it's spotted, let's say. Yeah? It's difficult not to spot it actually in flight, as pilot says. And if problem has been already identified, you still have enough lift to change situation. If even your ailerons, they are not so efficient now, you have another flight controls to work with. Or maybe some another means even additionally that we have not talked about yet. But if you're working with rectangular wing, the area of turbulence, it's closer to the center of fuselage, it's closer to the, you see this half of wings now, I hope you understand. And in case you're working with rectangular straight wing, in this case, it will be area closer to the fuselage, it will be greater, and it will be more dangerous in this case than in case of swept wing. So swept wing, somehow, at least with increasing, with higher values of relative narrowing of the wing, it's considered better in case of possible turbulence. And moreover, I hope you do remember about such things like winglets, deviated wing tips, that now became practically a standard of passenger aviation, as I already said sometimes maybe. And these winglets may help you to solve this problem partially with swept wing wrong downwashing, let's say, on high angles of attacks. So swept wing, in this meaning, it's like more preferable with respect to the straight wing, in case you have to decide which one. If you have variance, maybe use swept wing. Again, this angle of sweepness, angle between horizontal line with lateral axis of the airplane and leading edge. It's designated also with Greek letter C in our literature that you might see in Fedotov book, and it's maybe very different for different airplanes. Once again, the more speed, the higher this angle. How to choose this angle? How? You may analyze your prototypes, and by your prototypes approximately, you make decision. Angle of sweepness is in case you use swept wing. It's not all about shape of the wing. We have also dihedral, ahedral wings. I hope you do remember. In the front view, it's visible that in some cases wings are with tips up, and in some cases with tips down with respect to the horizontal plane. And all those decisions you need to do. But in these considerations about wing sweepness and wing straightness, what is also important to remember, and about wing aspect ratio. No, not sure that this picture explain you much, let's say, but I took those pictures, as I said you, in one of your books, and you may read it if necessary in more detailed explanation, but do forgive me, for you it's too much already. It's like not for first years. But you should remember about what? Swept wing, it's relatively longer, and at all, if wing ratio, wing aspect ratio is greater, wing is relatively longer, it will be heavier. Look at this diagram, it's given even to remind. Increased aspect ratio, wing aspect ratio, increases this lambda, dimensionless characteristic of the wing. Increased aspect ratio resulted in the increased weight of the wing. Next, after it will be really designed and calculated, what heavy wing is resulted in. The heavy wing, you do remember this beautiful formula of Majaysky? Heavy wing in absolute value. It means that it will be heavier mass of structure. Heavier mass of structure, it means that it will be heavier aircraft altogether. If this absolute value is greater, it's still half of the airplane supposed to be. But in kilograms, it became greater. And what happens then? It means that all takeoff weight you need to recalculate. Aircraft is heavier. After you recalculate aircraft takeoff weight, as you just have seen, what might happen? Yes, you need to increase wing area because heavy aircraft, you need another lift, you need another wing area. Circle is closed again, you see. No, of course, it's not so dreadful in real life. No, it's dreadful, but not so dreadful, like in my story. But do remember that it's permanently should be balanced. It exists the balance. The better, the more the better, or the less the better doesn't work really. And real aerodynamical characteristic, real aerodynamical performances, your aircraft as a whole, you might determine finally only knowing all the dimensions, only knowing all the shapes, like it has been already designed, at least by outer shapes, and creating the model of your airplane, scaled model. You may do test in wind tunnel. In this case, you will already awarded about the real characteristics of the airplane and wing and stabilizer and whatsoever, not earlier. But while the first steps, while the first iterations of design, it's necessary to consider factors, considerations that we are talking about. Right now, we talk about those considerations only in qualitative way. I'm trying to show you pictures, I'm trying to show you some diagrams, I'm saying something. But there are design books, no books for studying of design disciplines for students and books for engineers, which contain a lot of diagrams. And these diagrams show how that or another parameter will affect the wing, the airplane weight, the airplane flight dynamics, the airplane performances, and so on. So in real life, we have a lot of information, statistical information, scientifically taken information, which may help us to make decisions, of course. Now, in your design project right now, no, let's say design project, you limited only with information that you may take from your prototypes, from your statistical airplanes. And one more important moment also, when area, what here it's written, you see, да? So-called square cube law in aircraft design terminology. When area increase in square, when you increase some size of airplane, area, let it be a size of the wing you have increased, one of sizes. Area increased in square, but volume and weight of the airplane as together, it's increased in cube. No, I hope you imagine it, that actually whatever we think right now in plain picture in area, it has some thickness. And this thickness is determined by profile, shape of profile that we have decided, we have selected for our airplane. The greater size, the thicker profile. And when area increased in square size, the whole weight of airplane, because it's volume, it's increased in cube size. No, of course, it's also not so directly, but really you have seen my example with that trick with we took one speed, we took another speed for calculating the wing area, and you have seen how its effect to the parameters of airplane. Certainly not directly. It's not linear dependence. Well, once again, we have calculated wing area already. Wing area we have. What is next? Now, out of this wing area that we have calculated from weights, considering the weights of airplane, we need to understand absolute geometrical parameters of the wing. How to understand these absolute geometrical parameters? Using the idea that winged aspect ratio, again, you may calculate it, you may analyze it for your prototype airplanes. Wing aspect ratio, you take some particular value of relative elongation of the wing. Knowing your calculated area, you may say what span is. Knowing the area and span, you may calculate either mean chord or even immediately root and tip chord. You may appoint it, or you may use one additional parameter, relative parameter, dimensionless parameter, which is called narrowing of the wing, and also it means that you need to analyze your statistical information. And after this, we already have geometry of the wing, at least. So geometry of the wing, let's think we have finished with geometry of the wing. We're not finished yet, really, we didn't finish it. But let's think that we have finished it. What is next? Next, we have tail unit group. And seems like, again, we need to go to the dreadful story, you do remember? Airplane, ugly airplane, beautiful airplane, not similar to airplane at all now, sorry. Airplane with tail unit group, somewhere here, approximately. I forgot. We need to pick up to select some aerodynamical scheme, balancing scheme. No, let's think that we're talking about conventional scheme. When we have wing, we have stabilizer, and we have so-called stable scheme. It means that we need to place the wing in such a way that center of gravity, which we don't know where really, because it depends on a lot of factors. Center of gravity is in front of position of center of pressure of wing. Not the whole center of pressure of the airplane at all, but center of pressure of wing. And in this case, if it's conventional scheme, here is we have stabilizer. How to determine the area of stabilizer? Very simple. Very simple. What does it mean? It means that if you understand via the center of gravity, momentum of lift of wing to this so-called arm. No, let's call it L of wing. Better maybe to use little literal. Moment that create the wing should be equal to the same of stabilizer, because it's counterworking to another side. And there are three unknown values. What we really do know now? We know only this one, approximately. Not really, but approximately we understand it, yes? And that one is counteracting at all and stealing the useful lift. That is one more reason why Zhukovsky formula gave us some value, but that value was too little with respect to the values proven by real airplanes. It was less than necessary. Why? Because we forgot that actually we have here stabilizer that trying to steal some portion of our lift, and this portion may be rather high actually. What should be the area of stabilizer? Seems like it depends on how far stabilizer with respect to the lift. So for short airplane stabilizer, it's obviously, I hope, that if here will be closer to this place, force of stabilizer should be greater because arm is less, and it means that force of stabilizer should be greater, and it means that area of stabilizer should be greater. So quite clear, the area of stabilizer is also not simple task to choose. And what should we do in this case? Maybe you already have been perforated with this idea. You may analyze statistical data again. As for me, you may take approximately the area of stabilizer for your case in order not to overload you with calculations, with measuring, with analyzing stabilizer, fin separately. I propose you to take them for this game. 20% of wing area. So if we had, how much we had? 120, area of stabilizer will be what? 24. 24, and what are geometrical parameters of stabilizer? People, the same story. The same story, we may first determine, like if we think about some elongation of stabilizer, about this wing stabilizer aspect ratio now, this relative elongation of stabilizers, take some value, and you have span out of this value, out of area of stabilizer and out of lambda of stabilizer. The same you may do with fin, but do remember that in this formula you need to remember that next this span of fin, it's not span, it's like half span, because area of wing and wing aspect ratio, it was for the wing 2 halves of the wing, and fin you have only 1 half. Don't forget about this if you calculate. So do remember that fin is half, unlike the wing and unlike the stabilizer. And due to this, you already have geometrical parameters of wing, of stabilizer, and of fin. Have decided we are. But next we need to join them together. First, we do not understand how to join them in space. We have a lot of variants actually. Look, for instance, it may be, do forgive me, I need to drop it. Sorry. On one hand, it's maybe some in front view. It's a fuselage, and wing may be somewhere here. Low wing. Where stabilizer to place with respect to this one? Now do imagine here is, I will draw it and next we'll remove it, that we have a so-called relative wind downwashing the airplane. And on the wing, it start reflect like this. Somewhere in the area of wing, it's reflecting. We have seen the beautiful pictures. Let me not to find these pictures right now. We have it in those slides. And if I start again searching, scrolling, and so on, maybe it takes too much time, but I hope you do remember, approximately at least, the pictures of downwashing. I said, let me not to do it, and searching for them. Clever woman, do forgive me. What here is, no? We see that on the wing, it's already for turbulence, sorry. On the wing, it may be reflected down. Again, how we may know it? We have got this information. In wind tunnels, we have seen how shape of the wing, position of the wing, how its effect on that or another downwashing of the airplane as a whole. Look what I did. I have drawn, I have imagined, let's say, approximately right now, I have no opportunity to make wind tunnel for designs that I have not finished yet even, yes? And I approximately have imagined that according to the shape of the wing, and I understand that it has some initial angle of attack, it will be not parallel to the longitudinal axis of airplane. It's already on some predetermined angle of attack in order to increase its capacity of the wing. Downwashing approximately deflected by the wing. Here is some vortices, and it means that in this case, it will be more rational to move stabilizer higher. If we start checking the structures of different airplanes, what you will see, the stabilizer is, for low wing, stabilizer is typically higher than the wing. We may try to prove it right now with photos. What about if we choose high wing? High wing, fin. Do you imagine that wing is now somewhere here and stabilizer at the same place? Downwash them, and stabilizer will be on the way of those vortices that we on the way of the vortices that we have seen, as you remember. By the word, it's visible here, you see, high wing and T-shaped stabilizer, T-scheme of stabilizer. So once again, it's necessary to consider where to place in the top stabilizer and the wing. There are variants in this case. To remove this. Yeah. Variants, either you have T-shaped stabilizer, which is much higher than the wing, or if airplane is long enough, it's not little one, it's not short one. No? If it has long fuselage and it has high wing scheme, in this case, you may place stabilizer not like T stabilizer, but somewhere in this area. Because if it's high wing and stabilizer is somewhere here approximately, I mean long airplane, downwashing will goes low than stabilizer in this case. Once again, how to make decision in your case? Support yourself with prototypes. What do try to see right now what I said we might see in photos in order, it's not just my words. No, sorry, I was here in schemes, and one scheme we see, no? Airbus A318. No, let's take some another airplane, Boeing. The most known, the greatest in weight, 747-8 by now. Practically the same decision, you see. Low wing and stabilizer is higher. What about 737? Comparatively not big one. No, I need to see the front view. Here is, picture a bit different, but the same decision. Low wing and stabilizer is higher. Typically, I should say that in contrary to Antonov, that use high wing, no, they like traditions of their design bureau, they have high wing airplane. Typically, passenger airplanes use low wing scheme. Why? Because in case of, and these cases are well known, at least it was in the 17th in Leningrad, Soviet Union. Now it's called St. Petersburg, when airplane been landed to the water, passenger airplane been landed in the center of city practically to the water in order to save passengers. And it was landed some maybe 3 years ago. It was so noisy story when in New York, one of Boeing's been also landed immediately to some bay near New York to the water. They are not flying boats. They've been passenger airplanes with problem happened in flight, and this emergency landing in order to save passenger, they made on belly. It's called belly landing. But this belly landing was not to the ground, it was immediately to the water. And in case of belly landing to the water, in this case, you still have like support on the water for some minutes, and passenger have these some minutes to evacuate. So that is important consideration on one hand. On other hand, additional considerations. Where you're going to place engines? Look at this picture. What do we see here? Engines are under the wing. But what if we have high wing? Let's come back to our slides. We have high wing and we have engines under the wing because we have no another place, for instance, to place them. Where to? Engines under the wing, that is Antonov 148. I should say I spent a lot of hours in Antonov 24 when I was a child and teenager. People, it's something. After this flight, for some hours, you practically half deaf. You don't hear properly. Why? Because some meters from you, of course, it's not 1 meter, maybe it's 5 meters from fuselage. And of course, you're inside of fuselage. And of course, there is some noise protection inside of fuselage. It does not help much, I should say. No, approximately it was 40 years ago when I took these flights together with my family, of course, because I was a child and, as I said, a teenager. But I have something to compare. I've been in Tupolev 134, 154, which has engines in another place. Let me to show you two, for instance, 134 with two engines. Thank you. You see, now also low wing, but they have engines in the aft fuselage, not even in the aft fuselage, at the aft fuselage, on two sides of the scheme. Let's type drawing, maybe it's understand better. Oh, да. It has two engines on aft fuselage, aft fuselage on pylons, and they are behind of passenger cabin. The same, look, let's change one value here. But it's appeared the third engine. What here is, you see it, third engine, and it's also behind of passenger cabin. No? Behind of passenger cabin, and it's like inbuilt into fin. Actually, engine is not in fin. Here is only air intake, and engine is it's a little bit far there. No, it's possible to see in photos of the airplane. And one more, let's duplicate this page. Il-62 passenger airplane. We may check Yakovlev drawing, Yakovlev airplanes, for instance, and you will see the same decision, similar decision. Yakovlev 40 is two engine on pilots like it was in Tupolev airplane, and Yakovlev 42, it's already three engines. Look at this, I said. Four engines, you see? Even four engines, like a couple of engines from each side, and they are placed on these pylons. What it will be resulted in? It's important. No, I will try to explain it. What I try to show you. Copy water. In Paint, let's save these pictures for us in Paint or somewhere in Word might be. Next. Relative parameters of airplane. Look at this and let's take a look onto. No, I do not remember where Antonov already have hidden. Створити копію. On 140 drawing. Oh, great thing. Here it's very well visible. As for me, let's try to see the difference. No, not quite the same, of course, in quality, the picture. But difference, as for me, it's obvious. Look, no, Antonov 140 is for less amount of people, of course. That one is for higher amount of people. That is for less amount of people. That is why this looks thinner, like more slim. And that is why it's like more short, more puffy, more thick. Diameter of fuselage here even less than diameter of IL-62, to be frank. Diameter is next our story about. Pay attention, relative position of the wing. Moreover, it may be visible maybe on Antonov cargo airplane. Oh, look, Ruslan. Very beautiful picture. Seems like it start wing from neck immediately. What here is the picture. Let's copy it. And let's place it somewhere here to compare. By the word, very interesting picture have stolen occasionally. And do pay attention where the wing with respect to the length of fuselage in Ilyushin airplane. No, let's think it's approximately somewhere here, the middle of this middle chord. Yes. I don't know whether it's visible for you. I hope it's obvious for you. It's like pull it back. If we watch, for instance, Tupolev airplanes with engines at the end of fuselage, wing is far far from nose, somewhere closer to the end of the airplane. It's placed comparatively to Antonov high wings. Why? But look, Antonov middle of the wing is approximately here, and you see here is another proportion in this airplane. This place is shorter and this place is much longer. Wing is somewhere closer to the nose of the airplane. What it depends on? Balancing scheme. Once again, engines immediately here on the wing. Engines, they are so-called joined mass, joined weight of the airplane. If we even imagine that all other weight of airplane is distributed equally all over the fuselage, do you imagine that passengers or cargo is distributed approximately equally? Engines, wings, stabilizer, they are jointed masses, they are additional masses acting approximately concentrated somewhere along the fuselage. If engines moved here to this side, center of gravity also moved where? Where to? To this direction. Center of gravity moved in this direction, and somewhere not far from it, it should be center of pressure. So wing travel like following to the center of gravity, or no, in this conventional scheme, of course. It's like pulling front together with the center of gravity, because wings are heavy together with the engines. In case you place these engines to the back. Somewhere closer to the fuselage to make a more comfortable life of your passengers, for instance, to the aft fuselage closer. And what happened here? Wing together with center of gravity travel closer to the middle of the fuselage, even maybe far than middle of the fuselage. And in this case, lift should be also somewhere here after the center of gravity, we do remember. Yeah? But what it may be resulted in, look, there is no already place for no arm of stabilizer, long arm of stabilizer. Here, arm of stabilizer will be no counter force, you do remember. Yeah? Here is arm of stabilizer is long, and it means that you may take less area of stabilizer. In this case, you have to take more area of stabilizer when engines pull center of gravity back, seems like. More area of stabilizer, more weight of structure. No, it's obviously, yes. More comfort for passenger, but more weight of structure. If we analyze all the weights, if we analyze all the parameters with values, in case we have access to these values, I trust it will be obvious. Moreover, additional problem. I once already explained it about loading the wing in flight. And I hope you do remember, if we're talking about wingspan, if we have wing, not if, but when, sorry, we have wing. Bending moment, the most dreadful thing for the wing. Bending moment, it means that all the forces distribution, aerodynamical forces, they acting like this. And forces of weight, they will act in another direction. Approximately, it's also distribution with reducing to the end. Of course, it does not disappear here at the end because this tip also it has some weight. But somewhere here, it may be a sharp jump because of engine, yes? Additional jump of force. No, next is again distribution like this. What? Engine here adding the force. And what it will be resulted next, ugly picture, to forgive me, when we consider the not loads but external forces that appear in the wing during flight and during their, mostly we're interested during flight, of course, sorry. Internal forces that appear. What internal forces? Bending moment, as I'm already said, so the worst for us. Forces, so-called shear forces, they approximately correspond, their distribution, their diagram, the load diagram, approximately correspond to the external loads appear, general view. But bending moment at the tip of the wing equal to 0. No force yet. No force practically does not exist bending moment here. And the more distance to this place, the more bending moment at this place. And of course, that is the reason why we have weight, this geometry changing, like root is longer and tip is less usually by the word. Because at the root we need more massive inner structure to resist the bending moment. Okay, but bending moment for wing that is not loaded with the engine. But what if here it's joined the engine? What happened? And I even trust you do remember the pictures of A380 approximately on the ground and in flight, and the shape of wing was different. that it was brace-like on the ground, very beautiful, and it was completely straight in flight. What happened in this case? In this case, bending moment up to engine, its grows like this, yes, like it was, but where engine create counter moment, no, like this additional force has appeared. It's like counter moment creating. And it means that general distribution of inner forces will be like this. Maybe not so significant as I draw it, maybe. But at the place where you have engine, it's change this gradient. Its grows already not so significantly. And what it will be resulted in this place in terms of inner structure? It means that in this place you may use less massive structure, lighter in weight. So altogether, if you, as a period, when you place engine to the wing, altogether the structure of wing may be a bit lighter, less in weight. The same is stabilizer. No, you do remember that wing is on their wing. Do forgive me, engine nacelle, engine on the wing. Wing traveling front. By the word, let's check this idea about wing traveling front with foreign airplanes. Let it be Boeing once again. Boeing 747. No, because of big sweepness here, I would say it's not visible so significantly that airplane, no, anyway, it's visible in comparison to Illusion airplane. Let me to копіювати and to show you. If I place it here, what I hope for you it's obvious. If not, no, look, not so significantly. Approximately here they have chord, no, this root chord. Approximately here it has middle point of this chord, and where it has these distances. Comparatively to illusion that we illusion in question, let's say, where we have engines at the rear fuselage, this decision resulted in traveling of wing closer to the nose, shifting of wing closer to the nose, and due to this, you may reduce area of stabilizer, and due to this, you reduce general weight. But no, in Antonov airplanes, we have seen engines being placed under the wing, and it was high wing. Additionally, they have their, let's say, additional preferences in design, in reducing of the weight, and so on. But they have additional unpleasant moments due to engines, despite of any noise protection in cabin, in passenger cabin. It's not so pleasant flight for passenger, of course. All those various groups of factors, they affect on the choice of designer of the as to the airplane wing, stabilizer, fin, and where they, with respect to the middle area, like whether they are low wing, high wing, where stabilizer with respect to the wing, where what is the distance between them, how far they are from nose, and so on. While the first iteration for you, it's not possible to consider all these factors. Moreover, these factors, as I already said you, they are given in scientific diagrams, in special formulas, mostly those formulas, of course, empiric, but whatsoever, those formulas exist for designing of airplanes. And you are not able to do it. So you are relying upon the shapes and technical decisions of your prototype airplanes. No, maybe some of them will be not quite similar, quite clear. So work on your own then, decide what your airplanes better looks like. And look, I have proposed you either low wing or middle wing or high wing, but I have not proposed you mid wing. What is the reason for this? Once again, remind you, it has center wing, and the center wing is metal structure, rather massive. Let me to jump once again. Where is our slide we're working with? No, what here it's visible in high wing. That wing is continued practically through the fuselage. It's continued to another half. And like these two halves, they are met in the middle of fuselage, and it has the same structure here, this center wing. It has the same structure that is in the wing itself. And you understand that is the place of practically the most bend place, let's say, no, the place where we have the maximum of bend moment. And this place is very massive. It's maybe under the fuselage, over the fuselage, but if you select, for instance, mid-wing, what happens then? Then you have this structure that pass through the passenger cabin in case you have passenger airplane. It's completely inappropriate. It can't be like this. You understand it? No, like you have two separate airplanes, one with cockpit and first cabin, passenger cabin, and another with second passenger cabin, which does not not communicate immediately. It's not for passing from the nose to the rear fuselage, for instance, during flight. Two separate cabins completely in this case. So mid-wing, neither for passenger airplane, not for cargo airplane, they are not usable just because of these inner structures. For military airplanes, mid-wing is rather typical decision. Moreover, I have seen decisions for light airplanes, I mean structural decisions, for so-called business jet, for light airplane, when they have mid-wing, really. No, seems like it's mid-wing. But in this case, they have no center wing. And in this case, they have reinforced frames here, much reinforced frames, much more reinforced than in our picture right now, it's visible. And these reinforced frames, they, as experience again of designers show, using of those reinforcing frames resulted in increasing of the weight with respect of using the center wing in inner structure. So mid-wing with closing the loads to the frames, possible, yes, but in this case it will be overweight in comparison to another design decision of inner structures, even than low wing or high wing. Once again, for passenger airplane, higher wing maybe not good decision, especially if you use these engines below the wing, let's say, in front of the passenger cabin on some distance. And idea of crash landing, let it be, of emergency landing, also says that better to land to additional structure. In case Antonov airplane do belly landing, we are not talking even about water, not water, just to the field somewhere. Of course, landing gear in any case suffer. Landing gear may be broken, landing gear may be not even used, for instance. But Antonov airplane will land immediately to the luggage compartment, to the belly, yes? And airplanes that use low wing, like Boeings, for instance, Ilyushin, Tupolev, Yakovlev, they will land in case of emergency land, they will land to the structure of the wing. Seems like sound dreadful. Wing will be broken. Yes, but if it's emergency landing, wing of this airplane you will never already use. So no to cry about, let's say. There is no to cry about because wing is maybe broken. Okay, it's broken, so what? But passengers and cargo, no passengers above the all, we're interested in human lives. Passengers are okay in this case, or at least they have more chances, let's say, for surviving and for saving the health. Oh, maybe I was too long again. No, not long again yet, but I'm already too overlong, about to overlong. So let's come back to story about fuselage and composition of fuselage and wing with respect to each other. After interruption will continue. No, right now what we need to remember that after we know the area of wing, how we know it, I have reminded at the beginning. After we understand what is the area of wing, we need to calculate wing parameters. And for this, it helps us wing relative parameters. These wing relative parameters you may took either immediately in internet if you find it for prototype airplanes, or you may calculate it on your own. It's not difficult. No, wing aspect ratio, either you comparing the values that you have got, area and span formula you have seen. Let me to remind you once again. Oh, here is beautiful formula. Wing aspect ratio equal to span and area of the wing. These two characteristics, they are given practically always for airplanes and internet. Span, distance from tip to the tip, and area of the wing. So wing aspect ratio you may calculate even having no any idea about value of the chord, or if it's swept wing and it's difficult to calculate it somehow. In case you are working with the span already, you are able, again, understanding the area we have been calculated once, having the span, due to this dimensionless coefficient, you may use already the value of chord. If it's straight wing or slightly tapered wing, practically you already know all the sizes of your wing. In case it's swept wing, in this case, you need to go into additional constructions, let's say, and to work with so-called mean chord. Value that you may take as out of span and wing aspect ratio, for swept wing, it will be so-called mean chord, somewhere not even in the middle of the wing. We have seen it in explanation. I hope you understand. It may be closer, the thicker wing at the beginning, the closer this mean chord to the fuselage. Position and value of mean chord, it's easy to understand how to calculate it out of this. In case you'd like to pass from mean chord to your wing, if it's swept wing, it means that you need to use one more relative dimensionless coefficient, which is characterize the relative narrowing of the wing, and due to this, you may use you may already understand absolute values of root chord and tip chord. That is geometry of the wing. Next, we need to understand geometry of stabilizer, fin, and to place them in the proper place with respect to the wing. It's appeared too difficult for the first iteration, and what we have decided to do, either we analyzing the wing and stabilizer area for prototypes, their ratio, what is the ratio of wing and stabilizer, or just by my advice, take wing stabilizer area and wing fin area around 20% of wing area. And again, determine geometrical parameters of stabilizer and fin. Do pay attention, they may be quite different with respect to the wing, like long-winged aircraft may have rather short stabilizer, for instance, and sweptness of the wing and sweptness of stabilizer, they also may be different, and fin, they may be all different. Do pay attention to this when you're analyzing the prototype geometry, and make your own decisions, like what you finally select. What's the angle of sweptness in case you use swept one. And next, it's necessary to create fuselage. Even in such simple things like idea how to place wing and stabilizer with respect to each other, it's apparent that we need to understand where wing will be with respect to the fuselage, whether we select scheme of low wing or we select scheme of high wing. High wing, low wing, whatsoever, where to place engines. Engines for passenger aircraft, they can't be immediately in the fuselage. Quite clear that in fuselage you have people, you have passenger cabin, and you are rather limited in positioning of engines. Either you may place it below the wing or above the wing or somewhere at the aft fuselage. All the variants we have already considered. I hope you understood. There are no the best variant. No the best variants, and there is no the best variants, there are no the best variants because they are all resulted either in increasing the weight or reducing the strength of the wing, or in contrary, increasing the strength of the wing, uh, reducing the weight, but increasing the problems for passengers. Areas of real areas of stabilizers and real areas, their position with respect to the fuselage and to the wing, they also much depends on where you're going to place engines. On the wing, under the wing, inside the wing, like it was for Tupolev. That was one of reasons why I took as an example. Look at this picture 204 that I took as example in statistical data to show how it's deviate from another airplanes. Look to the picture. It has engine immediately inside of the root of the wing, you see. So where to hide engine or to place engine, that is also important question. And to pay attention that already next modification of it, 2124, is нет, that one it's yet with engine inside. Да. No, next modifications. They have quite different design in terms of placing the engines. People already been creating exactly passenger airplane, and they thought about the comfort of passengers. But that one, as I already said you, really it was redesigned strategic bomber. The strategic bomber, with another name, of course, quite clear that if they have no passenger cabin, they may place engine wherever, even inside of the fuselage itself. One more important consideration, where to place fuel. Typically, as I already said you, for passenger and cargo airplanes, fuel placed inside of the wing, inside of the fin, and if it's rather big airplane, also it's maybe placed inside of the stabilizer. Why I'm not for rather little airplanes, let's say, not for heavy airplanes and stabilizer, because stabilizer is thin in this case. It's practically no. Do take a look onto your palm. That will be thickness of stabilizer approximately, not even at the tip, somewhere in the middle. And quite clear, it's practically pointless to make additional efforts for making fuel tank there if you have so little volume inside of stabilizer. So stabilizer may be either empty or taken with some other devices, for instance. Well, and length and fuselage diameter we will discuss maybe after interruption of this record. Let's stop.